In this video, as you can see, we are going to take a look at accumulating more tools for your toolbox. Particularly, we're going to add integration strategies to the toolbox, and in this video, we're going to focus on integrating inverse trig functions as well as a strategy of completing the square. So let's take a look, and we're going to begin with a warm-up. If you are in my class, and this video is for 2021, so the page in your packet would be 14. If it's in a subsequent year, the page might be different, so simply find this page in your packet. What I'd like you to do right now is stop the video if you are in my class. After you hear the instructions. Complete number 1 and number 2 only. You have a prompt at the top that I'm going to read to you. Then I want you to stop the video. I want you to do number 1 and number 2 by yourself. And then I want you to resume the video to see how you do and where you need to correct your thinking, if anywhere. So here we go. The warm-up. Calculus, think about it, loves doing calculus problems. While completing his most recent assignment, he was able to do problems at a rate measured in yeats per utes. R of t is greater than 0 for all values of t. All right, so process what you are given. You have a student who is completing assignments. What we are given, pay very close attention to this. You have to process the information before you can respond. R of t is the rate at which he is doing his problems measured in some nonsensical units of yeats per utes. So at this time, I want you to stop the video. I want you to do problems 1 and 2, and then I want you to resume the video to see how you do. So let's take a look at problem number 1. In number 1, we are to write an expression for the average rate of change. So let's process that. We are finding average rate of change, and hopefully you recall that average rate of change can be replaced with the word slope. Algebra 1 slope. Change in y over change in x, and we're going to find the average rate of the R of t function. So specifically here, we should be looking at the change in R over change in time. Well, I guess utes are our time measurements. So what our expression should look like is a difference quotient, the rate at 11 minus the rate at 5 over 11 minus 5. Look carefully at the units. The units are yeats per utes squared. Why are the units yeats per utes squared? Well, let's take apart what we wrote. So in the numerator, R is already measured in, according to the prompt, yeats per utes. The denominator, which is time, so to speak, is measured in utes. So now we are dividing again by utes. So if you put that over 1 and multiply by the reciprocal, you can see that you're going to get yeats per utes squared for number 1. All right, I'm going to clear the screen and let's go to warm up. Let's just do a reset. Let's go to number 2. In item number 2, give me a second here. Get rid of that. Pull this back. Okay, that's better. In number 2, we are writing an expression for the average rate. Now notice in number 1, it said the average rate of change. This doesn't say the average rate of change. It says the average rate. Now remember that rate in our problem is R of t. Also remember that we've talked about in class that wherever you see average blank, we have said that you can safely insert the phrase value of. So if you do that decoding, you will see that we're finding the average value of R of t. We know that average value formula is 1 over b minus a, from a to b in general of f of x dx. So we are finding the average value of r of t. We're performing the average value formula, so to speak, on the function r of t from 5 to 11 units. So we are looking for, there is my divide by 1 over 11 minus 5. From 5 to 11, I'm accumulating the area under r of t dt. And let's think about those units. This time the units are yeats per utes. And let's figure out how those units come to be. So if you look at the 1 over 11 minus 5, we already established before that 11 minus 5 are the utes. So we have 1 over utes. And then the r of t itself is measured in yeats per utes. And then lastly, we have the dt. This is change in time, and our time in this case, they're nonsense units, but they are measured in utes. So think of this basically as multiplications, just like you do units in science work. These utes will divide out with one of these. I'll just do it over here, and our remaining units are yeats per utes. All right, and you're going to have more opportunities to practice those in upcoming lessons. So let's get on with today's lesson. You should have these, you should have in your packet, you should have the same notes that you see here, and you're going to fill in. So I want to process first, and this says warm up, so I guess this get warmer up instead of warm up. I want you to process the strategies that we have already developed and put into our toolbox. Remember that integration demands whatever strategy is needed to do the integration. There are very few alwayses. Well, the always is this. Always analyze the problem. Always evaluate what's going on and then make a decision about the strategy that you need to accomplish the integration. So far, what we have learned and what you have in your toolbox is you know how to reverse the power rule. And what I'm talking about there is a situation where there's no manipulation needed. So an example might be the antiderivative of 4x cubed plus x dx. So when you look at that problem, hopefully you realize I don't need to do any manipulation, I don't need to make any changes, there's nothing special about it, I'm going to reverse the power rule. And this is what I call a normal situation. You'll hear me talk about normal situations, and that's kind of in quotations because I use normal, and we'll talk about what I mean about normal. Basically, a normal situation is one that I don't have to do a whole lot of anything to, and it's not a use substitution situation. I just look at it and I pretty much know straight what to do. The second situation that second strategy that we have is reversing trig functions that need no manipulation. So in that case, we're talking about something like, let me get my pen here. We're talking about something like reversing, I don't know, secant x, tangent x, dx. There's no use substitution required. There's nothing fancy about it. You just have to do the anti-differentiation, your memorization of that trig integral. No manipulation needed. So that would be another situation that I call normal. You look at it, you just pretty much know what to do, straightforward. The third situation that we have encountered is we take a problem that maybe is quote-unquote not normal. In other words, you can't just integrate it automatically, but you can do power rule or trig after you do some manipulation. An example of that situation would be something like our take-apart or Miss Oliver problems that we work with. So if I had to find the antiderivative, let's bring back our 4x cubed plus x over square root of x dx. We're still not into u substitution at all. We don't have any fancy strategies or u prime over u or anything like that. We just have to manipulate algebraically, or in this case with our 4th grade math, we like to call it Miss Oliver math, our take apart, and then we can turn it into a normal situation. All right, our next strategy that you have in your toolbox is U substitution. So we talked about in U substitution when something has been done to our variable other than just plain x or whatever the variable happens to be, then we're going to need a U substitution. And so, for example, if I had, let's say, let's bring the one from the trig. If I had the antiderivative of secant 2x tangent 2x, now I kind of know what to do straight ahead, but I also realize that now I have an inside function of a 2x, and I'm going to need my strategies for U substitution. So it's a matter of analyzing every situation and deciding what you need to do. So so far, these are the only things you know how to do. It's either normal, it's normal after you manipulate, or you have to go to U substitution. And U substitution also includes our U prime over U. That's a sub-strategy of U substitution. We've also seen long division, although long division is an algebraic manipulation, and we think about long division if the power or the degree in the numerator is greater than the degree in the denominator. And then that might lead us to a normal situation, or it might lead us to U substitution. All right, so let's look at what we're going to introduce now. We're going to go back to inverse trig. Yay, I know you're really excited about that. I'm going to remind you that once upon a time, there was a group of students, and it was all of you, who actually knew what the derivative of inverse sine, or arc sine, it might be written, and inverse tangent. Hopefully you still remember that. I'm going to remind you that the derivative of inverse sine is 1 over the square root of 1 minus x squared. You actually knew that once upon a time. And the derivative of inverse cosine would simply be the negative because we have the co. Likewise, the derivative of tangent, once upon a time you knew it, is 1 over 1 plus x squared. So that's got to come back to the forefront of your mind because we're going to reverse. Now, as you can see over here on the right, I am going to find the antiderivative. So we're going to undo. Let me get my pen ready here. So we're going to find the antiderivative of this function, which is right here. And we're going to find the antiderivative of this function. You don't need to make these circles and arrows unless it's really helpful. But if we undo this and we antidifferentiate, we should get back, and we should get back. So you're going to need to recognize this, obviously, in reverse. These are things we have to have memorized. So if we undo the 1 over the square root of 1 minus x squared, we get inverse sine, don't forget plus c, inverse sine x plus c. And likewise with inverse tangent. So make sure those come back to your mind. And now we're going to step it up just a little bit, because in these situations, you notice we have the plain variable x and the constant right here. Constant here is a 1 and a 1, and a plain x and a plain x. Everything's great and grand. That's nice and easy. However, if we have, so look down here, compare, let me leave that in the screen. So compare what you see down here in number 3. So I'm looking right here. So in number 3, compare that to what you see right here. So these two, and be careful, don't draw these arrows. I'm just trying to show you where I am. Notice we have the same situation, except for now it's saying, well, maybe the constant is not going to be a 1. So we're letting a represent that constant. And maybe it's not going to be plain x. So when we see that situation, you recognize the pattern that it looks like arc sine or inverse sine or arc sine. And so in that situation, when you undo that, yes, you get inverse sine, just like we did up here at the top, except for when these numbers are different, we have u over a. And I'm going to explain and give you some examples. But for now, just make sure you get that formula and you start getting it into your brain. Same thing with the second one over here. When I find the antiderivative of a squared plus u squared, you can see, no pun intended, you can see that it fits this pattern right here. So that's going to bring us back to, no, oops, sorry, didn't mean to change the page. That's going to bring us back to inverse tangent, but notice what's happening. when the number is not, when the constant is not a 1, we have 1 over a, not a square, but 1 over a. And again, you're going to see this worked out in examples. For now, make sure you get the formula. And speaking of examples, let's tackle some problems. Strategies. So I left the formulas at the top just so that we can reference them. And the new strategy, what I just showed you, they're not really strategies. They're just memorization. But we're going to need a new strategy today. Dun, dun, dun. Completing the square. So I'm going to remind you and refresh your memory on completing the square and show you why and when we might need that particular situation. All right. It's not going to happen in number 1. So in number 1, we're going to start with our, look at your formulas that you have at the top of the page. And in that example, you can see of the 2 forms, so let me underline those for you. So this is the first form, we'll call it number 1 just to make it easy. This is the second form, we'll call this number 2 just to make it easy to reference. So when your math eyes look at, they're looking the wrong way, they should be looking that way, but anyway, I'm not an artist. When your math eyes look at the integration problem, which of the 2 forms does it look like? Well, it looks like number 1 because first of all there's a square root. Now you got to be careful that there's no plus in here, otherwise it's not that form. So you don't just look at the square root, you got to look at the whole thing. Now we have our formula up at the top and we notice that we have plain x, so that's great, but the constant in this case is not a 1, it's a 16. So here's what I recommend that you do, and I think this will make it easy for you. So what I want you to do is I want you to identify, so up here we're looking for u squared and we're looking for a squared. So in our problem, u squared is equal to x squared. Therefore, u is equal to x. Just taking the square root of both sides. Because you can see in my formula, I need u and I need a. Then I'm going to take the constant of 16. So my a squared is going to be 16. Therefore, taking the square root of both sides, a is 4. So I have my x and my a, and once I have my x and my a and I realize I have the correct format, I realize then that the antiderivative of this function is inverse sine of u over a. Here's my formula up here. Inverse sine of u, which is x, over a, which is 4, plus c. Don't forget the c, don't forget the c, don't forget the c. Okay, take a look at number 2, and based on what I just showed you with number 1, I'd like you to stop the video, I'd like you to follow that same process, and I'd like you to do number 2 by yourself and then resume the video to see if you get it correct. In number 2, let's draw a little line there, you can see that 1 over 4, I have a plus, I have the x squared, that fits format number 2. You can see up here that we're going to need to identify the a value and we're going to need to identify the u value. So take it slow and easy. So in this case, it's plain x squared, so u squared again is x squared. Take square root of both sides, u is equal to x. A squared, in this case, is equal to 4, therefore a is equal to 2. So once you know these, oh, by the way, well, I'll say that in a second. So the values that we need are here. So we follow the format. We have 1 over a, inverse, excuse me, inverse tangent, of u over a, which is x over 2 in this case, plus c. Now, the other thing that I was getting ready to mention that I haven't said yet, and I didn't mention it because our x is equal to u. We don't have any, we don't have to compensate for any kind of coefficients or anything like that. But one extra step that you're going to want to add in is after you find u and x, you want to take the derivative to see that du is equal to 1 dx. As long as du is equal to 1 dx, we don't have to compensate for anything or divide a coefficient over. And the same thing happens here. If I take the derivative of u, I get du, and the derivative of x is 1 dx. As long as we get the derivative to be 1 dx, we're good to go. And you'll see what I'm talking about in a subsequent problem. Let's move on to number 3. Oh my gosh, what the heck? So when you analyze number 3, first of all, the first thing I would do is move that dx to the back, and I will do that. So my rewrite here is the antiderivative of 1 over x squared plus 4x plus 5 dx. Just to get that off the top so you can see it better with your math eyes. This trinomial does not fit either of the forms above. Long division is not going to work because I have nothing to divide into. U substitution, the only thing I could do with U substitution would be let u equal to x squared plus 4x plus 5. du is equal to 2x plus 4. That ain't happening. None of that is in the problem. So U substitution didn't work. It's not normal. Some people might try to use the power rule on the denominator. That would be silliness. So when I have that trinomial and I don't have anything else to do, dun dun dun, complete the square. So over here on the side, I'm going to remind you the steps of completing the square. Now, I might not write down the words or the steps. You probably do need to write down the words or the steps that go along so you can start and stop the video as needed. So the first thing that I want to look at with completing the square, step number 1, and in your notes, just write a 1. Step number 1 is what I call kick out the constant. Number 1, kick out the constant. What does that mean? That means group the squared term and the first degree term together and kick out the constant, that 5. So still a plus 5. I'm just putting a grouping in there. I have not changed the expression at all in any way. Just put a grouping in there. So we're all good. Now, the next step, so that's number 1, kick out the constant. Number 2 does not apply in this case, but you need to be aware in our next example, if the coefficient of x squared is not 1. It is in our case, the coefficient of x squared is 1, so this is not going to apply to this example. If the coefficient of x squared is not 1, factor out the coefficient. You'll see it in the next step, but write it down for right now. If the coefficient of x squared is not 1, factor out the coefficient. That's the second step. Not going to apply here. All right, step number 3 is all about the need. I'm trying to figure out what I need in order to make this trinomial into a perfect square trinomial. The way that I do that is to determine my need is I'm going to take half of the coefficient of the x term, first power, first degree, and then I'm going to square that number. Half of the coefficient of x and square it. So for our example, the coefficient of x is 4, so we take half of 4 and square it. Half of 4 is 2, and 2 squared is 4. So that is what I need in order to force this trinomial to be a perfect square trinomial. Step number 4. Add, subtract the need. Add, subtract the need. Now remember, we can't change the value of this expression. We can't make it into a new expression. We can't change the value. So I can't just simply add a 4 into the problem. So what I can do legally is I can add, I'm going to put it back in purple to match the purple. So I can add the 4 on the inside. Now I have a perfect square trinomial, but I have changed the value of the expression. But to undo that, I'm going to subtract it out here with the 5. So now I've added 4, subtracted 4, So I haven't changed the value of the expression, I've changed the look of the expression. All right, so I'm going to clean that up right here. So now my new expression is, I wanted that to be blue, is x squared plus 4x plus 4, combine the like term, 5 minus 4 is 1. All right, so my next step, see if I have any more colors up here. My next step is to factor the trinomial. Hopefully this is all coming back to you because you've seen it in your prior math life. So when I factor the trinomial, it's always going to give me a perfect square. That's what we created. So I get x plus 2 times x plus 2. There's my factoring. And there's the plus 1. I'm going to do a rewrite. Since I have 2 of those, I can write it as a quantity squared. So I get x plus 2 quantity squared plus 1. And voila, the square has been completed. That's my completed square. So I did all of that work so I can do a rewrite of the original problem. Here's the original problem. So I'm going to come down here and I'm going to now make that the antiderivative of 1 over x plus 2 quantity squared plus 1 dx. Don't forget the differential. Now when you go back up to the top of your paper, hopefully you can see that that is a u squared plus a squared situation. So we're looking at this situation right here, except we just have a bigger variable. So let's do what we did above. Take a moment, stop the video, try to do as much as you can on your own, and identify a squared, u squared, and a and u. So a squared is the constant of 1. Therefore, a, by taking the square root of both sides, is equal to 1. And by the way, in case you're wondering, the order of these does not matter. Remember, this is addition. Addition is commutative, meaning you can change the order, in case that might be your question. All right, u squared, in this case, is equal to the quantity of x plus 2 squared. Taking the square root of both sides gives me x plus 2. So I have my u and my a. All right, so remember our formula above right now until you get it into your head. There it is, 1 over a inverse tangent u over a. So we have 1 over a, in this case is 1, so 1 over 1 is 1, inverse tangent of u is equal to x plus 2, and for emphasis, I'll write it over 1. You don't have to write the over 1, plus c. And that's how you complete the square. All right, I'm going to clear the screen and I'm going to go to example number 2, another situation of completing the square. You have your notes that give you the steps. And in this case, the difference in number 4 is that we do have that negative coefficient. We have a coefficient other than -1. So I'm going to bring and I realize it's in the radical, but I'm going to do my side work over here. I'm going to bring out the negative x squared minus 8x minus 15, and I'm going to complete the square. So step number 1, and it has to be in this order, is kick out the constant before you factor. So there's the minus 15 on the outside. Kick out the constant. And I advise you, I would encourage you strongly to stop and see if you can do it yourself. Step number 2 is if the coefficient is not positive 1, it's not, it's -1, factor out the coefficient from both of those terms. So that gives me a plus x. Step number 3 is to determine the need. So I'm going to take half of 8, which is 4, and then I'm going to square the 4, and I'm going to add 16. Now watch this. Don't watch carefully. It seems like I added a 16. Watch. It seems like I added 16, but notice I'm going to put a plus 16 out here. So I'd like you to stop the video and think about what he said in the last example, add and subtract, and he just added and added. Well, hopefully you stopped and thought about it and realized that even though this looks like I added, don't forget this negative right here. It applies to anything that's inside of that trinomial. So even though it seems like I added a 16, that's really a negative 16, and to compensate for a negative 16, we need a positive 16. So you've got to pay attention to those small, important, small, big things. I'll call them small, big things. So I keep my negative on the outside. When I factor, I get x plus 4 quantity squared, because square root, remember we created a perfect square trinomial. Negative 15 plus 16 is plus 1. So our new problem over here becomes the antiderivative of 1 over the square root of, now I'm going to write it in this order, it's okay, 1 minus x plus 4 squared. I think it's easier for you to see that it fits the pattern of arc sine when you put the 1 in front and then subtract. So our value of a squared is equal to 1. Stop the video and try it yourself. At any point, you don't need me to tell you this. You can do the problems and make sure you are understanding. U squared is x plus 4 squared. U is equal to x plus 4. So go back and look at your formula for the antiderivative, or to get back to arc sine. And so we have inverse sine of u, which is x plus 4, over a, again I put the 1 for emphasis, plus c. And you're going to get, obviously, to practice some of these. All right, let's go on to our next examples. Analyze number 5, and in fact, I don't know that I'm going to do all of these, but let's spend some time analyzing the situations. Not all of these necessarily are what we just learned. So look at number 5. Remember I said it's all about analyzing and making a decision and grabbing the right tool out of your toolbox. So take a moment to analyze and think about number 5 and think about what strategy you think we should use to anti-differentiate that. All right, hopefully you determined or thought about the fact that the power in the numerator is greater than the power in the denominator. So in this situation, I would use long division. So x squared minus 4x minus 2. Take a minute to stop the video and make sure that you can do the long division. I'm going to go ahead and keep going. So x times what makes x squared? That's going to be x. Multiply, multiply, that gives me plus x. That gives me x squared. And then I subtract the whole thing. Out, out. Negative 4x minus x is negative 5x. Bring down the 2. X times what makes negative 5x? Minus 5. Negative 5 times 1 is negative 5. Negative 5 times x is negative 5x. Subtract the whole thing. Out, out. Negative 2 plus 5 is a remainder of 3. So this problem is the same thing as the antiderivative of x minus 5 dx. Remember, we can separate. I would have the remainder over the divisor, 3 over x plus 1. Integral properties allow me to pull the 3 out of my way and get it in front as a coefficient. 1 over x plus 1 dx. The antiderivative of x is x squared over 2. That's a sloppy 2. Another sloppy 2. The antiderivative of 5 is 5x. The antiderivative of 1 over x plus 1 is ln, absolute value x plus 1 plus c. So part of this is to remind you that not every fraction situation is the same. Not everything turns into inverse sine or inverse tangent. Not everything is complete the square. You have to analyze every situation. All right, analyze number 6. Stop the video. Analyze number 6. Make a decision about the strategy you think you should use. Go ahead and work the problem out, resume it, and see if you get the right answer. In number 6, I noticed that the degree in the numerator is smaller than the degree in the denominator. I can't anti-differentiate as is, so I am thinking a u substitution. So I'm going to let u equal to the denominator. The derivative is 3x squared dx. I don't need that 3, so I'm going to divide it to the other side. It's looking pretty good. So that's going to give me a 1/3 antiderivative of 1 over x cubed u du. I think I got everything there. Yep. And so that will give me 1/3 ln absolute value of u plus c. But remember, I have to make my resubstitution, so I have 1/3 ln absolute value of x cubed minus 2 plus c. Same thing, number 7, make a decision, analyze, and move forward. So number 7 is a bit tricky. Hopefully you figured it out. If you did, you should be really proud of yourself. So I noticed that the degree in the numerator is smaller, so I'm not thinking long division. I could try u substitution. I think you are sophisticated enough now to think ahead and figure out that's really not going anywhere. Even if I divide the 4 to the other side, maybe we could think about stubborn x. Let's see. I'm sorry, I'm trying to talk and do the math at the same time. Never a good idea. Maybe we could think stubborn x, but like this, we still got this x cubed in there that we can't get rid of. So think about what you know how to do. You know how to anti-differentiate normal functions that don't need any manipulation, that you just look at it and go, oh, I know what to do. You know how to manipulate algebraically. You know how to do long division, which does not apply here. You know how to do u substitution, which didn't work. And the only other thing you know are what we learned today or reviewed today. Inverse trig. Seriously? Seriously. So watch this carefully. Notice, ignore the numerator for just a moment. Notice that in the denominator, I have the sum of 2 perfect squared. So I'm thinking, could it be possibly inverse tangent? I wonder. Let's identify. So the variable is x to the 4th, so we would say that u squared is equal to x to the 4th. Therefore, u is equal to x squared. Du is equal to 2x dx. Ooh. Divide both sides by 2, and looky, looky, looky. I have an x dx. Things are working out beautifully. Because if you look back at the formula for inverse tangent, actually it didn't have it. It's actually u prime in the numerator. I don't know why that formula does not have that there. Okay, so let's not worry about that. But I have the x dx that I can replace. If that's the case, then a squared in this case is equal to 1. Square root both sides, a is equal to 1. So since I have everything that I need here, this is the inverse tangent, inverse tangent format. So I get, what am I looking for? Oh, so we have 1 over a, and 1 over a would be 1 over 1, inverse tangent of u, which is, now be careful, u is x squared in this case, over a, which is 1, plus c. So that was a really tricky inverse tangent problem. Okay, so let's actually go back. I'd like to go back here and actually fix these formulas because I realize I'm not sure why. So go back to your formula page and let's fix this. When we have this in terms of u, this should be a du because I'm missing it. I notice now that I'm missing it in my integral. That's where I was like, what's going on here? So the du, so fix those. I didn't have the differential in there. I don't know if they got cut off or whatever. So I'm surprised I didn't notice that before. So that's why back here, when we had the du, there it is right there in the x dx is what we were, with the du, the derivative of the 2x. I'm not sure what I'm trying to say right now. I'm getting tongue-tied. Okay, take a minute to analyze problem number 8 and make a decision about the strategy you would use there. So in number 8, I am noticing that I have a higher degree in the numerator than I do in the denominator. I'm not going to do this out because I have done one already, but I'm thinking long division. So I would have 4x cubed. Now here's what I want you to pay attention to. Plus, since there is no squared term, I would have a 0x squared plus 5x minus 1. And honestly, I'm not sure I want you to even carry this one out. Maybe when I think when I set this up originally, we were just analyzing what we would do. Don't worry about doing the long division on this problem. I think it could get a bit messy. Not that it's not doable for you, but I'm just not going to ask you to do it. So this is your lesson on completing the square and the integration of inverse trig functions.